Here is a useful problem. Let's find the volume of a right circular cone in cylindrical coordinates. We're going to assume that the height of our cone is capital H, radius is capital R here. So we're looking for a formula here in terms of the height and the radius. Let's draw a picture. We need to, put our cone, in the X, Y, Z space here. So I'm going to draw our cone like this. So this distance right here, this is going to be the height. And then here is going to be the radius there. Okay, so we want to integrate, we're going to be integrating the constant 1 here over this region. So now we just need bounds on theta and R and Z. Okay, so it should be pretty clear here that theta, we want to do an entire loop around the circle. So our natural bounds, theta runs from 0 to 2 pi. But then, let's see, what else here? For fixed theta, r can be little r. The radius can be anything from 0 to big R. Taking a look here at the cross section. A cross section here looks like this. Little r can be anywhere from 0 to big R, 0 to big R. So then finally, we need to figure out what is Z? What is Z in terms of R? What is Z in terms of R? And so to do this, I'm going to pop out that little triangle right here. And so that triangle has radius R and it has height H here. And so this is like a sample value of little r here. And so our question then is going to be, well, here is the Z. What is the corresponding Z? And so we should see here similar triangles going on. That this triangle with little r and little z is similar to the triangle with big R and big H here. So that tells us that R over H is going to equal little r over Z. And then solving for Z in terms of everything else, Z is equal to big H over big R times little r. So Z is the height over the radius times the little r. Now we have Z as a function. Remember, generally speaking, we want Z as a function of theta and R. Here we have the Z as a function of R, so that's great here. So Z is going to be everything from, Z for fixed, let's be careful here, for fixed value of R, Z has to be from H over R times little r to big H. So once we have this as our R, Z has to be from here to here. So fixed this R value, Z runs from here to here. So those are our bounds on Z. And so all that's left for us to do is to say our integral is going to be theta runs from 0 to 2 pi, little r runs from 0 to big R, Z runs from H over R times little r to big H of 1. We're integrating 1 because we want to find volume. We still throw in the R, dz, dr, d theta here. Okay, and so what do we end up with? Okay, let's just evaluate this real quick. Integrating 1 here with respect to Z, I guess it's 1 times R, will give us Z times R, and we plug in Z is H minus h over r times little r times r dr d theta. Because there's no theta dependence anywhere in here, we can rewrite this as the product of two integrals. Theta runs from 0 to 2 pi d theta times integral little r from 0 to big R of h times little r minus h over r times little r squared dr. That's 2 pi right there. And then this is going to be, integrate with respect to r, h times r squared over 2 minus h over r times r cubed over 3. And plug in little r going from 0 to big R. 2 pi times, let's see, when we plug in r is equal to 0, that'll just give us 0. So the only thing we care about is plugging in little r is equal to big R. H times big R squared over 2 minus h over r times big R cubed over 3. That r cancels one of those r's. hr squared over 2 minus hr squared over 3. 2 pi times hr squared over 6. And this is pi times r squared h over 3. Which, if you know your high school geometry, that's exactly what we would expect it to be. That's exactly is the volume of a right circular cone with height h and radius r. So hooray, this all checks out.